Manometers are a direct application of the pressure-depth equation. They're used as an easy way to measure pressure, and they're both simple and inexpensive. A manometer is typically composed of a tube filled with a fluid. When the pressure on one side of the tube is increased, this pushes the fluid. When you measure the height difference, you can also calculate the pressure difference. So in order to solve for the pressure using a manometer, you must first obtain a starting point. In this case, our starting point will be B, which will be at atmospheric pressure. Then we will determine the secondary points. In this case, the secondary point will be A prime, which is located at a depth of h from B. The thing to remember is that since the pressure is the same at the same depth, both A and A prime will have the same pressure values. One thing to realize is that this is a simplification. We could go all the way down from point B to point C in the tube, and then from C to A, but the pressure increase from A prime to C, and then the decrease from C to A would be the same, so a simplification is made simply hopping from A prime to A. This will mean that the air on the left-hand side of the tube will have the same pressure as A prime. Finally, you can repeat as needed if there are several fluids in the tube, or if there's different bends. For instance, you might see this complicated manometer setup, and you might be asked to measure the pressure difference between A and B. So the question would be, knowing pressure of A, how can we calculate the pressure of B? First, what we want to do is we want to determine the locations of the boundaries between the fluids. So in this case, we have a boundary between water and mercury, mercury and oil, oil and mercury and water. Then we use the pressure depth equation ρgh to calculate the pressures at the different depths. When the depth increases, the pressure also increases, so the ρgh term will be positive. When the pressure decreases and the depth decreases, the ρgh term will be negative. An easy way to remember this is if you're moving down, it'll just be positive. If you're moving up, it'll be negative. Remember that the h's will change in each ρgh term, and so will the rhos. This is what the completed equation will look like. Pressure of B equals pressure of A plus density of water times gravity times H1 minus density of mercury times gravity times H2 plus density of oil times gravity times H3 minus density of mercury times gravity times H4 minus density of water times gravity times H5. As you can see, we're simply moving down, then up, then down, then up and up again in order to calculate the pressure differences at the different boundary conditions. Another example of this might be a manometer with different fluids, and in this case the process will still be the same. We start at our reference point, which is the open tube at atmospheric pressure, and then we work down and up again through the different fluids with different heights and densities. Another example of a manometer might be a manometer at an angle. And you might be wondering, why would this be important? This is commonly used in the real world to give more length to the tube for more accurate results, because for a small height difference, there might not be enough desired accuracy of the tube. Putting the tube at an angle gives the fluid more distance to go to rise a specified height, so the scientists can read more precise pressure values of the manometer.